Today we are going to discuss probability distributions. After this lesson, you should be able to use basic vocabulary, construct a probability distribution, determine whether or not a distribution is a probability distribution, and calculate expected values of a random variable. First thing I'd like to talk about is the term random variable. We need a definition. A random variable is a numeric value, such as x, associated with each outcome of a probability experiment. Some examples of random variables would be the number on a die when it's tossed, the number of attempts to shoot a free throw successfully, the number of times tails are tossed in 5 trials. And what you should notice is that every single time I'm listing an example, it's a numeric outcome of an experiment. So that is the key. It has to be numeric. A discrete random variable is a random variable that has a countable number of outcomes. You can have an infinite number of outcomes, but it has to be countable. So you could be counting from now until forever. If you can count them, if you can name the outcomes, then it is discrete. A continuous random variable is a random variable that has an uncountable number of outcomes, and it's usually represented as an interval on a number line. I'm going to start abbreviating random variable RV. It's a random variable that has an uncountable number of outcomes. It is represented as an interval on a number line. Now, here is a list of different random variables that I considered: zip code, temperature, height, weight, shoe size, and number of free throws until a success. I would like you to pause your video, try to decide which category each of these random variables can be sorted into, and then when you press play, you can check your answers. Okay. The ones that were discrete were zip code, shoe size, number of free throws until success. So you can count the zip codes. You could name the zip codes. Shoe sizes, same thing. 8.5, 9, you can name all those shoe sizes. Number of free throws until success. You may be trying from now until forever, but you can still count the number of times it will take. The continuous random variables were temperature, height, and weight. You'll notice in between any two temperatures, there is yet another one. So if you had 21 degrees and 22 degrees, there's 21.5. If you look at 21 and 21.5, there's 21.25. I can always find another value in between any two. Typically, continuous random variables represent some sort of measurement. A discrete probability distribution is a chart that lists all possible values of a random variable with their associated probabilities. There are two requirements. The first is that all probabilities are between 0 and 1, and the second is that the probabilities sum to exactly 1. Here are 3 examples of potential probability distributions. I'd like you to check each of these and decide which one or ones represents probability distributions. Press pause on your video, and when you're ready for the answers, press play again. Okay, the only one that was a probability distribution was the first one, and that's because all of these are between 0 and 1 and sum to 1. If you look at the second one, this is not a probability distribution because I have a probability that is over 1. This is not a probability distribution because it does not sum to 1. Now, this is an example of creating a probability distribution. We're going to let X represent the number of heads tossed and create a probability distribution for X. So we're tossing a coin 3 times, and we want the number of heads tossed. The lowest value number of times we could toss heads would be 0, and the highest number would be 3. So we might get 0 heads, 1 head, 2 heads, or 3 heads. So we're going to use our skills from our last section to figure out the probabilities for each of these. So if I want the probability that I don't toss any heads, remember this is an and probability. None of them are heads. So the first is not, and the second is not, and the third is not. So we're tossing all tails. 1/2, first is not, and the second is not, so we're multiplying, and the third is not. Oops, I wrote a 3. And the third is not. So if I multiply all those together, I get 1/8. Now, the probability that I toss exactly 1 head, you have to remember it could be heads, tails, tails. It could be tails, heads, tails, or it could be tails, tails, heads. So there are 3 ways for that to happen. And the way we can figure that out is I have 3 tosses, and from those 3 tosses, I'm going to choose 1 that is heads. 3 choose 1 is 3, which is what we just counted on our own. So again, 3 choose 1. The probability that the first is heads is 1/2, times the probability the second is tails, another 1/2, times the probability the third is tails, that's another 1/2. So I'd have 3 times 1/8. This is 3/8. Now, if I can make this larger. Oh, good. So, maybe not. Oh, off to the side. So now I want to know the probability that X is equal to 2. Well, this time I'm going to choose 2 heads and 1 tail. And rather than it being this way, it's going to be like this. I could have heads, heads, tails. I could have heads, tails, heads. I could have tails, heads, heads. So again, there's 3 ways. The way we can count that is saying, well, I'm tossing the coin 3 times, and of those 3 times, I'm going to choose 2 of them to be heads.